Welcome to Dr. Jimmy's Business Calculus in Section 4.4. I'm going to bring up exponential functions, different than the polynomials and those types of things we've been looking at. And then, what about the derivatives? Y equal 3 to the x is an example of what we call an exponential. So this is an exponential function. Although 3 to the x, we could say, well, it's a power expression, just like x cubed. But in the context of variables, we call x cubed a power, and we call 3 to the x exponential. And the difference is that the variable is an exponent when we talk about exponentials, and the variable is the base when we call it a power. So although they're similar, a symbol with an exponent, it depends on what's varying, whether we call it an exponential function or a power function. So power functions we looked at and had certain characteristics. Okay. Basic shapes of powers are somewhat like halves of parabolas that come down and have a slope of 0 at some point. Or, in the case of parabolic type of shapes, a vertex. In other things like x cubed, a point where it does have this flat tangent characteristic and then grows without bound as you move away. So, now we're going to look at the exponential types. So, if we look at y equal 3 to the x, and then consider graphing some points. At 0, the value is 1, which for a basic exponential, if we make the exponent 0, 3 to the 0 or any base to the 0 would have been 1. At 1, it's 3, at 2, it's 9, at 3, it's 27. So we see that as we progress through and allow x to approach infinity or become larger and larger, we notice that 3 to the x also becomes infinite. Or we have the limit as x approaches positive infinity of 3 to the x is infinity out of that. If we continue with some negative values like 1, minus 1, then we get 3 to the minus 1, but that's 1 over 3. At minus 2, 3 to the minus 2 would be 1 over 9. At minus 3, 1 over 27. So we have these same numbers, 3, 9, 27, and so forth, but the reciprocals. So the observation that if we let our x become a very large negative number, minus 1, minus 2, minus 3, minus a million, minus a billion, we're observing that 3 to the x is becoming smaller and smaller. And so closer and closer to 0. So we see a limit for negative values becoming extremely large of 0 for 3 to the x. So, a quick sketch. Let's see. So at 0 we have height 1. At 1 we get height 3. At 2, well, we're already high enough I can barely graph it. So at 3, way high. And then at -1 we're down to a third of height 1, and then a ninth, and we can hardly tell after that point. So we have this shape of growing without bound if we let x become large positive, but extremely close to 0 if we let x become negative. So we have this basic exponential shape, but if x gets bigger, this graph gets bigger. It's sometimes called exponential growth. So it grows exponentially. Okay. And then the fact that the limit is 0 for x approaching minus infinity is, as in the picture, asymptotic behavior of y equals 0. The x-axis is an asymptote. So that's our basic exponential picture, and this one exponential growth. But if we take a number like 1/3 as the base, okay, it's actually 3 to the minus x, if I want to write it that way. So an exponential, but a coefficient of the exponent now. So if we looked at it graphically, we would have had the 3 to the x with exponential growth. 3 to the minus x means that every value that was positive x gets moved to the same height at minus x. So if we take the graph of exponential growth and revolve it around the y-axis, we have a picture of 1/3 to the x power. So now the base is small instead of larger like 3, and we get exponential, what's sometimes referred to as decay. So exponential k, this base was less than 1. All bases will have to be bigger than 0 to get it defined for enough x's. And the exponential growth the base has to be bigger than 1. Base equal to 1 is a special case because it's just the straight line y equal 1. But otherwise, if the base is a number like 3 or something bigger than 1, this is exponential growth. If the base is less than 1, it's exponential decay. Okay. Growth or decay, it's asymptotic. It's just in a different direction. So asymptote y equals 0 in the exponential decay, just like growth. So those are the characteristics of exponentials. They have this feature of becoming very large and infinite in one direction, sort of like powers, but only one way, and asymptotic, so quite different. There's no place like a vertex, or there's no slope of 0 anywhere. So, basic exponential is y equal b to the x. And so b will have to be a positive number to define this. And we get growth when b is bigger than 1, and decay or decline, b is less than 1. Now, if we look at the exponential and consider a derivative, so again, let's use a specific base, say 3, and look at the definition. So y prime, in this case, we would take the limit of a change in x, h, becoming extremely small. And so we would take the change in the functional values, evaluating at x plus h, compared to what it was at x. So that difference over the change in x. So change in y over change in x, take the limit. Rules of exponents, we can break 3 to the x plus h into a product of 3 to the x and 3 to the h. And then we can factor out the common factor, 3 to the x. The 3 to the x is not affected by what happens to h. So that would be the same effect either before or after we do the limit. And so we end up at this setting where we have the original function, 3 to the x, times a particular limit. This limit is independent of the value of the x, whatever it is. So, now at this point, we'll accept the fact that there is a particular limit. So if h goes to 0, 3 to the h minus 1 actually exists. So now, so what we've found is that y prime is equal to a constant, whatever this limit is, independent of the x, times the original function. Or in the case of an exponential, the ratio of the derivative to the function is constant. So they're proportional. So, for exponentials, such as 3 to the x, the observation here is important, that the derivative compared to the function is a constant. What does that mean? Well, the way it's changing. The relative change is directly proportional to how much there is. So y would be the original how much, y prime is how it's changing. So how it changes is directly proportional to how much there is. So that's an important real-world model. Things like if you put air in a balloon and there's a hole, how fast it comes out, that is the change, is proportional to how much air is inside. If you have financial markets, how fast things change is proportional to how much you put in to the market. Okay? Less going in means less change. More going in means more change. So exponentials end up being one of the very important models of real world and real world data due to this study. Now, if we study this limit, accepting that it actually exists, somewhere in the possibilities for different bases, we get a different limit. But somewhere in there has to be a place where we can pick a base such that that limit is actually equal to 1. And for that reason, it's a very generic to all of these exponential growth, decay being proportional to the amount present. It's actually known as the natural number. Okay? So it's so prevalent in the world, in models, this number is distinguished. It's sort of like pi. It's this ratio of the circumference of a circle to its diameter. So it became an important fixed constant. That's not a nice whole number. The natural number is this one, where we have all these settings where how it changes depends on how much it is, what it is determines what it does, those kinds of situations. And so the generic setting is if that proportion is 1, and that base that causes that is called the natural number. And we have a symbol E. So just like pi has a special symbol, the natural number has a special symbol E. So for general exponentials of some base, the derivative is the original exponential times this limit, which is some constant. When that limit's 1, it's base e. Now, a little more, and we'll get to this later, is that limit actually is what's known as the natural log of the base b. So we'll get and go back and review logarithms and things a little later, but at this point, if you can just write down natural log of some number, or you can get a decimal approximation on most calculators, we won't be using properties of the logarithms at this point, just being able to know that this is a constant, or we could get a decimal approximation. So we have that general rule, but if we take the exponential with the natural number e, the derivative is the same exponential. The natural log, or that extra limit factor, is chosen to be 1. That's how e is defined.